Good morning, everybody. Thanks for joining this talk about plasma cleaning. Today, we're going to talk about different techniques that you can use to monitor this process. Before we go into the details of these techniques, I want to cover the basics of the plasma cleaning process so that everybody is on the same page. The first thing that I want to discuss is the fact that the goal of the plasma cleaning process is to remove surface contamination and to leave a surface which is ready for the subsequent process, which can be either a molding process, a wire bonding process, or anything where adhesion is critical. When we talk about surface contamination, the most common thing that we want to remove are organic components. So you may think that your products are clean, but actually, on the microscopic scale, they contain different levels of contamination. The organic contamination sticks to your products because it cannot evaporate from them because the contamination has a low vapor pressure. Let's talk about now, for example, how an argon plasma can remove organic contamination from a product. As we just said, the organic contamination cannot escape the product because it has a very low vapor pressure and cannot evaporate from it. What we do is that we take this dirty product and we expose it to a plasma cloud. Inside the plasma cloud, we have different species. The first one, of course, is the argon atoms, which are neutral. And then, of course, the key players, which are the argon positive ions. These species can interact with the contamination as they are accelerated towards it. And when they are accelerated toward the contamination, they exchange physical energy and start breaking down the contamination. When I say start breaking down the contamination, what I mean by this example is that we have heavy organic compounds, very long, which do not evaporate from the surface. Once the argon ions interact with them, they exchange energy, and if this energy is high enough, it can break chemical bonds. When we break chemical bonds, the byproducts that we obtain are very light, and they are so light that they can escape the surface, go into the plasma cloud, go into the vacuum that we have inside the plasma chamber and escape through the vacuum pump. This is the principle of the plasma cleaning. Taking organic contamination, breaking it down so that it can evaporate from the surface, and then removing these byproducts that are generated during the process by removing them through the vacuum pump. Now that we have the basics of the plasma cleaning covered, we can move to the first set of monitoring techniques, which are the on-product measurements. The first thing, which is for sure the most known, is the contact angle measurement technique. This is used to characterize before and after plasma cleaning states, and it's typically done with deionized water. It's an easy technique to apply. We take a tiny drop of water, very tiny, about 0.2 microliter. It can be 0.1, it can be 0.5. It really depends on the product. And it's placed on top of the product surface. Then we take a photo of this drop from the side. And as you can see, this is what we may obtain as a photo. What we need to do now is to determine the angle between the drop profile and the product surface. To do that, we trace a line, for example, where the drop touches the product, and then we trace the tangent line to the drop surface, like this. Once we have these two lines, we can then calculate the angle between them, which is, in this case, for this example, 67.2 degrees. Angles above 50 degrees signify that the water does not like to stick to the product very much. It much rather would stick to itself. This means that the surface is slightly hydrophobic, and this is caused by the organic contamination that we have on top of the surface, which we have to remove with the plasma cleaning process. So before plasma, values between 60 to 120 degrees are really common on dirty products. When we start from this and we apply plasma, what we obtain then is something much different. In this case, as you can see, the drop profile for the same volume is a lot different. The drop likes to stick to the product so much that it is spread thin across the product surface. And now if we do the same exercise again, we measure a contact angle of 10 degrees. In general, contact angle values below 40 degrees after the plasma cleaning process mean that the plasma cleaning process was successful, that the surface is actually clean. Sometimes you can spec less than 10, less than 20, less than 30. All these values are specific to the materials. Some materials are very easy to clean, and so you can specify very low contact angle values. Some others are different or simply like the water less. And so you will not be able to reach less than 10 degrees, but if you reach less than 30, you're already sure that the surface is really clean. So what we expect after the plasma process is angle values below 40 degrees. If we get these values, we have an indication that the surface is hydrophilic and it's clean, and that the organic contamination has been successfully removed. So contact angle measurement is the first technique. It's really important because it's easy to apply. It can be done in a production environment because it only requires the contact angle measurement machine. And it's in general a production-friendly technique because it's really fast to do this. You can sample your product, you can do process development with this technique very fast, and it can give you results pretty fast. The second technique that I want to talk about involves the use of surface tension active inks. These inks can be purchased on the market. And again, they are used to characterize a before and after state. What's important about these inks is that they can be bought at different specific values of surface tension. This means that I can buy and I can use one of the inks at 30 or 72 millinewton per meter. And since I know the surface tension of the liquid, what I'm going to do is that I'm going to try to paint the surface of my product before and after the plasma process. And if the ink can stick to the surface, this means that the surface has at least the surface tension value mentioned on the ink. So if I take the 72 millinewton meter ink and I try to paint my surface and it sticks, that means that my surface has at least 72 millinewton meter of surface tension. Practically, what this looks like is that we have two different outcomes when we try to paint. The one on the left, the surface tension is not enough, and so the ink will try to form tiny drops. Or the surface tension of the product is high enough to have the ink stick to it. And so we know that the product has been cleaned correctly. Again, this is a very, very simple technique. It can be, these inks can be taken into clean rooms and very quickly verified if the product after the plasma process is cleaned correctly or not. And they are a very, very simple and effective way of checking if the process is running. The second set of techniques that we can use to monitor the plasma process involves checking and verifying that the plasma process parameters are within bounds. So we can see here on the right a diagram of a plasma chamber where we have a product inside. Of course, we have the vacuum pump to go in vacuum. Once we are in vacuum, we can introduce our process gas, for example, argon. And of course, we need to connect this to a power source to generate the plasma. So in general, the plasma can be ignited with an electromagnetic field. This can be a DC field, a low frequency, radio frequency, or microwave field. That doesn't really matter. The plasma will have different characteristics, but at the end, what we're trying to see here are the parameters that we can monitor. If we focus, for example, on the process variables of RF plasmas, which are the most common in the industry, we know that we can verify and measure the reflected power, which is the power that goes back to the generator from the chamber because there is an impedance mismatch. The self-induced bias, which is a property defined by the geometry of the system, by the gas, by the pressure, the configuration, and the surface area, or the pressure, which is the most direct and easiest to monitor. If we talked about the reflected power, so we measure the amount of power that is transferred from the RF generator to the plasma load. If any of this power, for example, we want to have 300 watt transferred and we get back 10, this is the reflected power. We want this value to be as low as possible, meaning that all the power that we have decided to use for this plasma step goes into the plasma and cleans the product. So what we can do is that from an engineering point of view in the machines is to measure the reflected power, monitor it during the step where the plasma is on in the machine, and if this value is above a certain threshold, for example 50 watt, the machine will stop and say, okay, the plasma is no longer delivering the results that we want because there is a lot of reflected power. And so the machine will stop to avoid sending downstream product that have not been cleaned properly. So we can continuously check this, and if the value is above a certain limit, we will stop the process and inform the operator. The second parameter that we can monitor is the self-induced bias. The self-induced bias is a negative voltage which can be easily measured inside the RF tuner. The important thing is that this voltage is proportional to the plasma potential. And so it's proportional to the plasma intensity, how good the plasma process is. And so what we can do is that once we define a certain process at the R&D level or at the process development level, when we introduce a new product, for example, we see that we have negative 100 volts. And so we want to be sure that throughout the production phase, we always get this 100 volts. So the lower this voltage is, in general, the higher the intensity of the plasma is. So if we have negative 100 volts and after a while the machine gets dirty, we didn't do the maintenance with the correct frequency, or something goes wrong because something breaks inside the machine, there will be differences in this voltage. And instead of having minus 100, we're going to get, I don't know, minus 20, which is much less. And so if the value gets too close to 0, it means that the plasma is no longer working. And once this happens, again, the machine should stop. What we can do, we can implement techniques to monitor this value during the plasma step. And again, if we go over a certain threshold, the machine can stop and inform the operator that something is not working correctly. The third parameter that I want to talk about is the pressure. Pressure is extremely important because it defines how the plasma interacts with the product. The pressure can be easily measured with a pressure gauge, and maintaining this pressure throughout the plasma step is really, really important. For physical plasmas, the pressure needs to be low because we need to be able to accelerate the ions of the plasma with a certain energy, and we want to be consistent in doing so. If our process with argon has been defined at 0.1 millibar, we need to be sure that this is consistent throughout the production runs, so that the ions are always accelerated with the same energy, and so we get consistent results at the end. For chemical plasmas, instead, the pressure needs to be high, in the sense that it needs to be into a higher range between 0.4 and 2 millibar, for example. In this case, chemical plasmas, they work differently. Chemical plasmas are generated with oxygen, nitrogen, hydrogen, and all these polyatomic gases. In this case, we don't need to accelerate ions. We want to produce a lot of radicals, and these radicals are the key players. They will migrate to the product surface and chemically react with the product contamination. So we need to think about this as if it was a chemical solution. The more concentrated the solution is, the better will be the end result. And so for plasma, that since it's a gas, we're going to talk about pressure. So in general, what we need to do, no matter the type of plasma that we have, the configuration or the end result that we want, monitoring the pressure is extremely important, and staying in the good ranges is very, very important. What we can do for each process, we can define, okay, this process needs to run at 0.2 millibar, and we can say we allow it to run between 0.15 and 0.25, because this is the range that works for us. If for any reason the pressure is too low or too high, the machine should stop and alert the operator. So this is the third and very important process variable that needs to be monitored in process. The conclusions that we can draw from these short talk are the following. We have available to us different measuring techniques to determine the effectiveness of the plasma process. We can either measure directly the state of the surface of our products before and after the plasma process. This can be done by using the contact angle measurement technique. So using a tiny drop of water, taking a picture and measuring the contact angle, or this can be done by using surface tension active inks by trying to paint the surface. There are also other advanced techniques that can be used in the process development phase, and these are techniques like SEM for morphology or SEM EDX for measuring the surface composition, anything related to surface spectroscopy with Raman or with XPS, for example. These advanced techniques, we didn't have time to cover them. They are used typically on the R&D and process development phase, where we have more time and we want to try to understand exactly what's going on the surface. But in a production environment, they are not very useful because they are expensive. They are long. It's long to obtain results from them. And so contact angle measurement and surface tension inks are the most common and most production friendly. The second thing that we can use is measure physical properties of the plasma. And these are reflected power, self-induced bias, and process pressure. These are the very three most common and most important properties. There are other things that we can do, but if we have a hold on to the reflected power, the self-induced bias, and the pressure, we are almost 100% sure that the plasma process is working as we want it to work. If we implement both strategies, they have a very low cost of adoption, but these allow us to be sure that our plasma process is consistent, delivers the result that we want, and is stable for a production environment. With this, we reach the end of the talk. Thank you very much for staying with us in this talk, and we are always available to discuss technical details of the plasma process and plasma applications in general. Thank you very much.